Hey there, physics class. I hope you're having a great time working on your Rube Goldberg machines and had a good time with that yesterday. And so today we're going to talk a little bit more about conservation of energy, which goes right along with that, because the idea is that if you have your system in your Rube Goldberg machine and you put energy in once, the energy is not going to be lost or gained. It's just going to be changing forms as it goes from one place to another place as it moves along the line. So that's what the idea of the law of conservation of energy is that throughout the time that this whole thing is happening, and if it's a closed, isolated system, and that energy isn't going to be lost, it's not going to be gained, it's only going to change form. When we are doing some of our most basic type, we don't take into account like food stored or battery stored up energy or things like that. We can talk about just the mechanical energy, and the mechanical energy is when you put the kinetic and the gravitational potential energy together, and that is fantastic in being able to solve a whole host of different types of problems that we're going to be talking about. If there's nothing else present, so in other words, no heat being generated from friction, and you've got a system where there's nothing else going on, then you can have the idea of mechanical energy being conserved. And for the most part, that works really great, although every system does have some kind of friction to mess with it a little bit. But we can, for the most part, deal with that conserved mechanical energy, and that will help a lot. When we need to calculate how much mechanical energy there is in a system, and usually we're just thinking about one moving object here, we've got our kinetic energy, and our kinetic energy added to our gravitational potential energy equals how much mechanical energy that particular object or thing has. So we can do problems based on that. Okay, when we use this type of an idea, interestingly enough, if you have a hill or you don't have a hill, or you have something that's being shot up into the air, and you're not talking about rocket boosters or anything like that, so projectiles, or if you're talking about something that has a really steep drop or something that has a very gentle drop, and the height differences are the same, conservation of mechanical energy does not depend on things like how steep the hill is. It does count how big the drop is, but not how steep the hill is. So we have this great thing going on where the kinetic energy and the potential energy, when you add them up before, they have to equal the kinetic and the gravitational potential after. So this would be like the key thing that's going to help you to do all of your problems. So you need to make sure that you write this down. Kinetic before plus gravitational potential before equals the kinetic after plus the gravitational potential after. And so sometimes it fools us into thinking that we've lost some potential energy or kinetic energy, but we haven't ever really lost it. Sometimes there's air resistance or friction, which actually kind of absorbs some of that energy. The friction, when that is happening, you've got some heat generated, which is another kind of energy. So it is a change in form. So that's why your numbers don't always work out. The mechanical energy is conserved for the most part, we can say. The total energy is definitely conserved, and that's a scientific law, but the mechanical energy can sometimes, part of it, change form over into friction. So we're going to look at some example problems. So you're going to want to either write this down or print out a blank copy from your page on the notes section. we'll talk about this large chunk of ice that's falling from a roof that's 8 meters above the ground. We want to find the kinetic energy when it reaches the ground, and then the speed of the ice when it reaches the ground. So we need to think about that idea of the kinetic and the potential energy coming together and then changing forms. So our kinetic plus potential before equals our kinetic plus potential after. So because it's not moving when it's up at the top, it has no kinetic energy. But the potential, remember, is mass times 9.8 times height. We can assume that the ground is 0 because that'll be our easiest thing to do. So we're thinking about our ground level as being 0. So we got mass, gravity, height right here. Here's our mass, gravity, height. I need to get rid of this part. There we go. And then on the other side, we have our kinetic energy plus 0. 0 for kinetic here because it's not moving. 0 for gravitational potential here because it's made it to the ground. And the height is 0. Mass, gravity, height. Height is 0. So kinetic energy after the fall equals what the potential was before the fall, as long as it all got converted. Okay, so all of that energy changed from being gravitational potential to kinetic as the chunk of ice was falling towards the ground. Our measurement, as we know for all energies, is in joules. Mass, gravity, height, but 0 potential at the end. It has all been converted into kinetic. So the speed, remember our kinetic energy formula is K equals 1/2 mv squared. So here's your kinetic energy. Here's your 1/2 and your mass and your velocity squared. Do a little bit of calculations here. If we take half of 15, we get 7.5. 1,176 divided by 7.5 gives you this, and then square root it, and you get about 12.5. So your speed at the bottom is 12.5 meters per second. Now, we've done problems like this before. We've done it in terms of having those equations where you're trying to figure out the speed, assuming that 9.8 is your acceleration, and those equations all still work, but this is another way of finding the information having to do with the conservation of energy, and it's kind of a nice little slick way of doing it. So you do need to know how to do this. Now, the next few examples we're going to do match up with your practice problems 9 through 12, which you should be working diligently. Hopefully you're combining your work time a little bit on the Rube Goldberg, a little bit on the assignments. This is a longer video today, but just keep it going. So we have a skateboarder that's coming up on a hill, and they're going 3.5 meters per second. The mass and the rider of the skateboard together is this, and we need to find the starting kinetic energy of the rider and the skateboard. Now, we're making a slightly artificial scenario where the skateboard rider, we're just talking about they're already in motion, they have their velocity, they're on the board, both feet on the board, and they didn't push. They're just going strictly by their momentum to get this. So we're going to think about the skateboarder on the board going that fast, finding the initial kinetic energy. Okay, so kinetic energy, 1/2 mv squared. So we need to figure that out. 1/2 mass of the rider, velocity squared. And you do your calculations and find out that you have 483.9. You should be very good at doing that type of a calculation. Now, this is the new part. He coasts up the hill, and assuming there's no friction, we want to know how high he's going to come to rest. Not necessarily this way, but how high this way. Not necessarily how long the ramp was, but how high up off the ground that the skateboard rider is when he comes to rest. Okay, he's not putting his foot down, no brakes, just gliding right on up there. So for that, we have to keep in mind this idea of the kinetic plus the potential before has to equal the kinetic plus the potential after. And this, of course, being our gravitational potential. So beforehand, we know that before he goes right up that hill, he's got 483.9 joules of energy. That's kinetic. Potential, he's at the bottom of the hill, so he has 0. Mass, gravity, height. The height is 0, so therefore his potential is 0. At the end, he came to rest. 1/2 mv squared. When the person has come to rest, you've got a 0 here, so that gives you 0 kinetic energy. At rest means no energy of motion. Plus UG. UG is mass times gravity times height. 79, 9.8 times the height. So you're left with a simple equation to solve. Multiply these and then divide this by what you get. Don't forget to pause if you need to make sure that you're getting a chance to think these through. It's better if you're working right along with, so lots of pauses there, and then however you're working at your pace. So when you multiply, we get these, divide 483 by 774, and you get 0.63 meters, and that's how high up that skateboard rider will be. Not particularly very high, not really going very fast, so the coast is only going to get him up almost to 1 meter in height. Now, we want to think for a minute whether or not the answer to part B depends on the mass of the rider. And that's an interesting thing to consider. Because when we really consider what happened before and what happened after, this is 1/2 times 79 times 3.5 squared. This is 79 times 9.8 times h. 79 is his mass. But since the other parts are 0, you could really, if you wanted to, cancel the 79s out on both sides. So our answer to that is no. Part B does not depend on the mass. Here's what I was talking about. Here's our kinetic. Here's our 0 doesn't count, 0 doesn't count. Here's our 7.79 times 9.8 times height. The 79s could cancel out and we're still going to get the same height out of it. So if you're good at it and you're good at plugging things in, the mass part doesn't even matter. In this case, and I say in this case because we've got these zeros, all of the energy transferred over, so it doesn't matter because all the energy transferred. Okay, so we've got to be careful to make sure that we don't assume that's always the case, just when only all of it transfers over. Looking at another question, we've got the bowling ball, and the bowling ball, it's suspended from a ceiling and on a chain. Okay, well, where in the world would I think of something like that? Well, that's actually something that has been talked about before. There's this scenario where a professor did this and pulled the bowling ball back, and with the idea that since energy can't ever be lost or gained, that if they let it go and let it swing as a pendulum and come back, that it couldn't possibly hit him in the face as long as he just let go of it. So the scenario kind of went into a moral thing, as if you saw him imperceptibly put a little push on that ball and was standing there with his face ready to not get hit, but you knew he put in a little bit of extra push, a little extra energy, knowing that it was going to come up and smack him in the face, would you say anything? And of course you would, because you're good people. But anyway, that's where this scenario came from. You've got a bowling ball of mass 6 kilograms suspended from the ceiling on the end of an 8-meter chain. It's like a pendulum. There's a problem in your book that uses that same idea, but it's not a bowling ball. It's something else that's suspended from something and swinging and becoming a pendulum. And so the student pulls the ball back so that it's 1.5 meters above the floor. And you've got in your picture of your mind, it's going to come swinging down. We want to know how fast the ball is moving when it reaches the floor. So we need to use that idea of conservation of momentum once again. So kinetic energy before plus the potential before equals kinetic after plus potential after. At the beginning, the ball is not moving, so we have a 0 here. At the end, it reaches the floor, so there's no potential, so we have a 0 here. So those zeros don't count. Mass, gravity, height, 1/2 mv squared. So you can do your calculations here. And when you do the calculations, you end up with v squared equals 29.4 square root it. You get 5.4 meters per second. Now here's the thing. We're asking, does the answer to part A, does the velocity depend on the mass? And let's think this through. You've got these zeros, they don't count. There's a 6 on both sides. You could do the same problem if you canceled out the 6. So no, it does not depend on the mass. Does the answer depend on the length of the chain? Did we use the 8 anywhere? No, we didn't. So no, it does not depend on the length of the chain. It only depends really on how fast the thing, how high up the thing was pulled, and then that will determine how fast it's going at the bottom. In this case, all of the potential turned into kinetic. In the last scenario with the skateboard rider, all of the kinetic turned into potential. So they can go back and forth. So a follow-up to this could be you've got the ball went down to the bottom, and then in order for it to all get changed back into potential, it's only going to get up to the height that it started at. And then it could swing back and it'll change all into kinetic down here and then all into potential when it came back up here. And the kinetic would be gone. So swinging back and forth. Theoretically, in that thought experiment with the professor dropping the bowling ball down and coming back, he should be perfectly safe. He's not going to get hit in the face. If he's standing here and this O is his face and he lets that ball go and he just lets it go, it's going to come back and it's not going to hit him in the nose and he's not going to get knocked out. All right. Don't try it at home though, because it's pretty dangerous, because that person could get their teeth knocked out if they put a little push in it, gives it a little extra energy, then it's going to have more energy to come back and come to a higher height. Okay. All right, so another one is roller coasters. Traditional roller coasters way, way, way back in the day weren't the ones that had turbo boosts in the middle of them. Traditional roller coasters literally were coasters where they would be pulled up to the top of a hill, and then it was the gravitational potential energy was getting changed into kinetic energy as gravity pulled it down. And it would gain its speed just simply because it got pulled to a very high height to start. So there had to be some energy to pull it up to its starting point, get its potential, and then when it let down, it would gain its speed simply because of the coasting roller coasters. Okay, so we want to know how fast it's moving at the bottom of the hill. So that means our problem starts at the top of the hill and it ends at the bottom of the hill, before and after. So we're keeping into our mind the idea of the kinetic plus the potential equals the kinetic plus the potential once again. Our kinetic at the top is 0. At the bottom, we have some kinetic energy. At the top, we have the greatest potential. So this will be a number, mass times gravity times height. Mass 200, acceleration due to gravity 9.8, and the height 15 meters. And then on this side, kinetic energy 1/2 mass 200 v squared, unknown v, and a potential is down to 0. Now this particular problem, once again, the 200 doesn't really matter for this part of the problem. And then when you do your calculations, you end up with velocity being about 17.1 meters per second. Now, as far as the speed at the top of the next hill, now this is an interesting scenario because at the top of the next hill, it's only going up to 13 meters. So it's not losing all of its kinetic energy. It's keeping some of it. And it doesn't have quite as much potential as it had before it started. So it's got, this one we're not having any zeros at the end of the problem. So that makes it really very interesting because only some of it got transferred over. So here, when we're thinking about the before conditions, we're looking at kinetic energy as being what we had from our 17.1 meters per second. So 1/2 200 times 17.1 squared. The gravitational potential is 0. So we have that half of the equation. Let me get this so we can see it a little bit at a time. Okay. So we've got 1/2 mv squared here. And our gravitational potential is 0. The kinetic at the end, though, 1/2 mv squared. We don't know our v. And then our gravitational potential, mass times 9.8 times height. The height now is 13, though, instead of 15. We need to include that in our calculations. Okay? So our velocity part, this is not going to be 0 because it's not going all the way up to the height to where it was before. So we need to do some solving here. We figure that part out. 1/2 of 200 is 100. We have this part of our equation. We can subtract that from both sides. We can divide by 100 and then square root it and get our new velocity as being 6.1 meters per second. Okay, so 6.1 meters per second is how fast this thing is going at the bottom, not at the bottom of the hill, at the top of the next hill. So at the bottom it was going 17.1 and then it loses some of its speed when it goes back up, but not all of its speed. Now another interesting thing is that if you wanted to, you could even forget about the middle part and you could use this beginning kinetic and then you could make your other side of the equation this same thing for ending and it would give you the same answer. It's very interesting because all of this mechanical energy has been saved. It's been conserved. So you can do a problem such as that without even considering the bottom of the hill. But it's still good to consider the bottom of the hill because the bottom of the hill is the exciting part of the roller coaster where it's going fastest. So that's where I want to stop us for today. Okay, so your job is to continue working on the practice problems 9 to 12. I would rather have you do that than more Rube Goldberg because your Rube Goldberg projects needs to percolate in your mind a little bit and you need to think about it. And then on Monday, you're going to be doing your Rube Goldberg. That will be your whole job on Monday. And then Tuesday, I'll finish the lesson on, well, I'll work on the Chapter 11, Section 2. and then we'll keep it going, keep it going, keep it going, so that you're getting chapter 11 finished up while you're working on Rube Goldberg. All right, so there's that, and I hope that you have an amazing weekend. Do make sure that you try to get through questions 9 through 12, and God bless you.